Okay, so we are now on page 74, number 13. All right, so the question says, does the function f of x equals x cubed ever have a negative slope? If so, where? Give reasons for your answer. Now, so step number one, sorry, my computer's asking me to save the previous one. So yeah, there we go. I'm going to take, and this is not how I would want you to answer the question ideally, because you can certainly give me an algebraic answer, which we're going to look at. But sometimes when you're uncertain about something, y equals x cubed is something you know how to draw, really well, or should know how to draw really well. And, this could be used as an answer, might not necessarily get you full marks on a test. But even the graph kind of tells you, well, hey, look at the slopes of the tangent. If you try to draw any tangent, always seems to be positive, with one exception. At zero, that's, it could be that at zero it seems to flatten out. So maybe it's zero, maybe it's not, but it's definitely not ever going to be negative. Okay, so you can give an easy graphical justification, but even better would be to give an algebraic one. Now, what is it that algebraically gives us the slopes of the tangents of any function? Well, it's its derivative. In this case here, we've already found the derivative of x cubed. So unless you're being told to find it from first principles, this is something we've already found from first principles. So there we go. We have 3x squared. Okay. And what do we know about 3x squared? Well, 3x squared can never be negative. Okay. If you really want to, you can draw your little number line, and when x is less than 0, pick x equals -1, this is going to be positive. Pick x equals 1, still going to be positive. So 3x squared is always greater than or equal to 0. Okay, so what's your conclusion? Hence, f at x never has a negative slope. Negative slope tangent, sloped. Terrible English, but you know what I mean. Okay, so here, again, this is kind of giving us a window into what the derivative function can give us. It can give us these general properties of how the rate of change behaves in a function, because now we have an actual equation that gives us any rate of change whenever we like. And so we can make these sort of grand statements like x cubed is never going to have a negative rate of change. Okay, does that answer the question?
Yeah, thanks.
Yep, okay, good. So hold on, there was another one that was thrown in, 4717. Okay, so let's look at 74.7b. Okay, and these might be, looks like these are probably going to be our last questions, these last three, okay? So page 74, number 7b. All right, so here again, they're asking us to find this thing, which of course we know is the derivative of the function y with respect to x, okay, from first principles. So for first principles, that just means from the actual definition. So it's another way of asking the same question that we had in number 6, where they said find it using the definition of the derivative. First principles means the same thing. So in this case here, what is y equal to? Y is equal to x plus 1 over x minus 1. So another function where we don't have derivative rules yet. We don't have that, we're hoping we're going to have a nice quotient rule. We certainly don't have one yet. Okay, so dy dx, if I want to use this notation, is going to be equal to the limit as h approaches 0 of the function evaluated at x plus h. So notice here, it's this that's getting replaced by x plus h and plus 1. this variable is getting replaced by x plus h. And now minus 1, minus the function evaluated at x, so just the function itself, all over h. Okay, and here, well, we're going to have to, do a lot of work. We're going to have to subtract those two expressions. So here, what's my common denominator? Well, it's just going to be x minus 1, x plus h minus 1. Okay, I'm going to save myself a step because I know that dividing by h is like multiplying by 1 over h. So the h is just going to end up in front there. And now I have to do the work of this doesn't have the factor of x minus 1 in the denominator. So it's going to be x minus 1 times x plus h plus 1. This here does not have the denominator of x plus h minus 1. So I'm going to have to multiply by x plus h minus 1. All right. And now we're going to have to very carefully write everything out. Okay. So this is going to be x squared. Okay. Here we're going to have plus xh. Then we're going to have plus x. Then we're going to have minus x. Then we're going to have minus h. Then we're going to have minus 1. Okay, so I hope everybody's checking my algebra. If you spot something, please don't wait till later on to say, hey, Tony, shouldn't that be a negative? Okay, please make sure you're looking at what I'm doing here. So x times x, x squared. X times h plus xh. X times negative 1 minus x. Here, 1 times x, 1 times h, 1 times negative 1. Sorry, what did I do here? I think I was doing this too fast here. Sorry, x squared, this should be plus. No brackets there. Again, why did nobody stop me? Folks, I need you to keep track of what I'm doing, please. Okay. All right, so I'm not convinced I did this. I want to check this one yet again because x squared plus xh minus x. Okay, that's good. Plus x plus h minus 1. Okay, looks good, but I feel better that I checked it. All right, so now let's see if we can got x squared minus x squared. Okay, here I have an xh, then a minus xh, so that's gone. Here I've got an x minus x, that disappears. Negative x plus x, that disappears. Negative 1 minus negative 1, it's negative 1 plus 1, that disappears. So it looks as though the only thing I'm left with out of all of this stuff in the numerator is negative h minus h. So minus 2h. And hey, that's good news. The h's cancel out. So I'm just left with negative 2 over x minus 1, x plus h minus 1. And now I can take the limit, because here this is x minus 1, and this is x, this is approaching 0, another x minus 1. So I'm just left with x minus 1 squared. Okay? So again, very important to be very careful. If you're uncertain about anything that you do, give it a quick check before moving on. Okay, it'll pay dividends when you get to the correct answer. All right. So again, the thing to keep in mind, folks, is number one is to understand how to apply the formula for the derivative. Once you've written this out, there's not much in terms of calculus that's left over. It really is. So the definition from first principles, remember, is the derivative of a function, whether written in this form or that form, whatever form you write it, is the limit as h approaches 0 of the function defined at x plus h minus the function defined at x all over h. This is what we mean by the formula, the derivative, first principles, the definition, all refer to this here. Okay? So what we started off as the rate of change, what we talked about the rate of change, when we identified it as this limit, we started now using the term derivative, okay, which is that function which produces the rate of change at any point. Okay, is that good? Just confirm before I move on. Yeah, okay, good. Anybody else on this question or anything on the definition of the derivative? No, okay. So now let's go back to 47. 47. Okay, so 47. So first at 15b. Okay, so 15b, I suspect we might have to do, well, actually, I don't think we need 15a to do 15b, but let's have a look here. Okay, so this is page 47, number 15b. Okay, now here again, we have to make sure we're looking at the information that's given, and here they tell us that the limit as x approaches 0 of f at x over x is equal to 1. So you know that limit exists. And they tell us that the limit as x approaches 0 of g of x over x is equal to 2. And in B, they want us to determine the limit as x approaches 0 of f at x over g of x. Okay? And this is a very nice question because it sort of forces you to find a connection between what you're looking for and what you're given, okay? Because you're given information about limits that involve f and g, but not directly about f and g. What you're told is the limit of f at x over x, the limit of g of x over x. So what you would like to do is in this limit, can you recreate these two expressions so that then you can use them? Because once you get the expression f at x over x, you know that limit exists as x approaches 0. You know this limit exists. So the question is there any algebra you can do legally to this expression that would produce both of the ones we see in the limits that are given? Does anybody have any suggestions? It's actually something fairly simple. What could you do to this expression so that you'll end up with an f at x over x somewhere and a g of x over x? I would actually say, so what do you mean multiply? Because what are you multiplying? Because x over g of x, you'd be changing the expression. Limit x over g of x. So maybe I'm not seeing, so actually put another limit inside the limit? Is that what you're suggesting? Ah, I mean, not, we could, but boy, that's a lot of, that's complicating things. Okay, there's something much, much simpler. What could I do to this fraction? Ah, there we go. One thing I know I'm allowed to do with fractions is to multiply numerator and denominator, or divide numerator and denominator by the same number. So why don't we divide the numerator by x and the denominator by x? This is a perfectly legal operation. Now, just in case you're thinking, but wait a minute, oh, you can only do that if x is not equal to 0 and I'm approaching 0, so why is that not a problem? Why do I not worry about the fact that x can be equal to 0 in principle? Oh, not because it cancels out? Because now I just added something that doesn't exist at 0. Why is this of no concern to me? Yeah, partly. We're taking the limit as x approaches 0. What is the one thing I care nothing about? I don't care what happens at 0, exactly. Okay, so this is why this is a perfectly, we don't need to worry about it, because what happens at 0 is of no concern to us. But look at what we have. Does the limit in the numerator exist? Yes. Does the limit in the denominator exist? Yes. So what do the limit properties allow us to do? Split up these limits. And oops. Because not only do the limits also exist, does the limit in the denominator approach 0? No, it doesn't. Okay. And Karma, maybe tomorrow, come and show me maybe I just wasn't understanding what you were saying. So if you remember, just come and show me so that maybe what you were doing works. Okay. Okay. And so now the limit in the numerator is 1. The limit in the denominator is 2. And there you go. 1/2. There's your answer. Okay. Oh, sorry. It says if you multiply f at x over x, it's the same thing, but x's cancel out. Well, you would just have to say that that only works out as long as x is not equal to 0. So when you're simplifying rational expressions, you're allowed to use that, as long as, um, you say, this works only if x is not equal to 0. But in this case here, we don't care about x equaling 0. So that's why we don't have to add that little, okay? So again, Abe, if there's an issue, just ask me tomorrow. Yeah, Karma, show me tomorrow, just because I don't want to look at it now. It's going to take too much time, but just come and show me tomorrow. Okay. All right. Um, all right. Any other questions on this here? No. All right. So let's take a look at the last question here. Is 17. Oh, phew. I'm glad nobody asked me number 16, because I would have said, go check it out on your own. It's long. No video on 17? Anybody check? Okay, so let's take a look here. Page 47, number 17. Okay. So here, let me write this out carefully. If you have the book in front of you, just check that I'm writing this out. So x squared plus x minus 1. X minus 1 minus 1 all over x minus 1. Okay, and they're asking us if this limit exists. You can sketch it by, I'm not going to, unless it's really easy, I might not sketch it. I'll have you look at it on Desmos. Okay. Now, again, I'm going to take the time to write this as so if I call this f at x, let's write it as a piecewise function. Okay. And obviously 1 is going to be the key value here. So here, let's take x is less than 1. Okay. And what's going to happen here? Well, the x squared doesn't change. Okay. Because this thing inside is negative, I'm going to have to put a negative in front to make it positive. So I'll be adding this negative. Again, make sure you're putting brackets. Okay, and minus 1. And then in the denominator, same thing, put a negative in front to make it positive. All right, and now for x greater than 1, okay, these things are already positive inside the absolute value, so they will not change. So x squared plus x minus 1 doesn't change. And then here, again, x minus 1 does not change. Okay. So let's see what happens here. Well, I have x squared minus x. Okay. And now I've got positive 1 minus 1. Okay. So the ones cancel out. Okay. And here, what happens, we have x squared plus x. And here, minus 1 minus 1 minus 2 over x minus 1. Okay. But now there's clearly lots of factoring that can go on. Okay, so let's take out an x here. We have x minus 1 minus x minus 1. Ah, nice stuff is going to happen. Here, that factors in 2, so I need it to add up to plus 1. Okay, so it's going to be equal to x plus 2x minus 1. And again, more nice stuff is going to happen. And then finally, these cancel out, so I'm just left with negative x. Okay, here these cancel out. I'm just left with x plus 2. All right, so it was a bit of a journey, but we got there. Okay, so now if I'm taking the limit as x approaches 1 from the left, I'm going to be taking this function here. Okay, I'm just saving myself some time to just put it straight in. And so what's this approaching? Just negative 1. Okay, and now if I'm taking the limit as x approaches 1 from the right, what is it, x plus 2? It looks like this is just going to be approaching 3. Okay, so limit does not exist. Okay, and now graphing this will be pretty easy because look at how simple they are. So again, I'm going to use my trick of just saying, okay, negative x, okay, looks like this, and in fact, it's going to 1, so that's pretty easy. It's 1, I'll do that, and then x plus 2 is just going to look something like that. Okay, I guess I should specify here that that's 2. And there you go. So again, it's about just carefully identifying how you're going to rewrite the absolute value based on whether the inside is negative or positive. So when it's negative, you just stick a negative sign in front. If it's positive, you just leave it as is, and then carefully simplifying your expressions. All right, any questions on this? All right, so let me stop the recording.